Let's get straight to it. Can an effect happen before its cause? The idea feels wrong. It breaks a fundamental rule of the universe as we know it. You throw a rock, the rock hits a window. The window shatters. That's the order of things, cause then effect. The throw, the impact, the breaking. You can't have the window shatter and then decide to throw the rock that broke it. Our entire experience of reality is built on this forward-moving arrow of time. We remember the past, not the future. We make choices that shape what's to come, not what has already been. This is causality. It's the law that says A has to happen before B can happen. If A is the cause of B, it's so basic, so woven into the fabric of our world, that questioning it sounds like nonsense. It's like asking if you can be born before your parents. The logic just doesn't work. And yet, in the strange microscopic world of quantum physics, this simple, unbreakable rule starts to look a little shaky. Scientists, a group of people who are usually very careful with their words, have run experiments that are hard to explain without at least considering the possibility that, in some very weird way, the future might be able to influence the past. This idea has a name. It's called retrocausality. It doesn't mean you can send a text message to yourself yesterday telling you the lottery numbers. Well, it's not about science fiction time travel. It's something much more subtle, much stranger, and much more confusing. It's a question that pokes at the very foundations of what we think space, time, and reality actually are. To understand why anyone would even entertain such a bizarre idea, we have to talk about how things work in our normal, everyday world. Our world is governed by what we call classical physics, the physics of Isaac Newton. It's the physics of billiard balls, planets orbiting the sun, and glasses falling off tables. It's predictable. If you know where a billiard ball is, how fast it's going, and what direction it's moving, you can predict exactly where it will be in the next moment. And the moment after that. In this world, time only moves forward. Another important rule is entropy. It's the idea that things tend to go from order to disorder. An egg is a very ordered thing. You scramble it, and it becomes a disordered mess of proteins. You can't unscramble an egg. A pile of sand is disordered. You can build an ordered sandcastle, but the wind and waves will eventually turn it back into a disordered pile of sand. This increase in disorder is a one-way street. It's another reason why time seems to have a direction. The universe as a whole is becoming more disordered. That's the arrow of time we experience. A shattered glass is more disordered than a whole one. You won't see the shards spontaneously leap back together to form a perfect glass. So, our intuition and the physics of our daily lives scream that retrocausality is impossible. The past is fixed. The future is unwritten. The present is where we act. Simple. Clear. Except it's not the whole story. The trouble started about 100 years ago, when physicists began to explore the world of the very, very small. The world of atoms and the particles inside them, like electrons and photons. Down there, the comfortable, predictable rules of classical physics break down completely. This is the realm of quantum mechanics, and it is a place of deep weirdness. One of the central ideas in quantum mechanics is that tiny particles don't behave like tiny billiard balls. A billiard ball is in one place at one time. An electron is different. Before you look at it, an electron doesn't have a definite position. It exists in a kind of haze of possibilities. It's a wave of probability spread out over a region of space. It's potentially in many places at once. Only when you perform a measurement, when you look at it to see where it is, does the electron decide to be in one specific spot. The act of observation forces it to choose. This is strange enough. But it gets much stranger when you look at one of the most famous experiments in all of physics, the double-slit experiment. Imagine a wall with two thin parallel slits cut into it. You set up a device that shoots tiny particles, let's say electrons, one at a time toward this wall. On the other side of the wall, there's a screen that detects where each electron lands. If you cover one slit and shoot the electrons, they go through the open slit and hit the screen behind it, forming a single band. No surprise there. If you cover the other slit, the same thing happens, but the band is in a different spot. Again, makes sense. Now, what happens if you open both slits? You might expect to see two bands on the screen, one behind each slit. That's what would happen if you were throwing baseballs. Some go through one slit, some go through the other. You get two piles. But that's not what happens with electrons. Instead, you get a pattern of many bands, a series of bright and dark stripes called an interference pattern. This pattern is a hallmark of waves. Imagine dropping two pebbles into a pond. The ripples from each pebble spread out and interact. Where the crest of one wave meets the crest of another, they add up to make a bigger wave. Where a crest meets a trough, they cancel each other out. The interference pattern on the screen is exactly what you'd expect if the electron wasn't a particle, but a wave that went through both slits at the same time and then interfered with itself. This is the core mystery. A single electron, all by itself, seems to go through both slits at once, like a wave. But when it hits the screen, it arrives as a single particle in a single spot. It behaves like a wave when it's traveling and like a particle when it's detected. But the real mind-bender, the part that opens the door to retrocausality, comes next. The physicists, being curious people, decided they wanted to know which slit the electron actually went through. To do this, they placed a tiny detector at one of the slits. This detector could tell them, yes, the electron just passed through here. The moment they did this, the interference pattern vanished. As soon as they started watching the slits, the electrons stopped behaving like waves. They started acting like normal, well-behaved particles. They went through either the left slit or the right slit, but not both. The pattern on the screen went back to being just two simple bands, exactly what you'd expect from throwing baseballs. It was as if the electrons knew they were being watched. The very act of measuring which path the particle took changed its behavior. It forced the electron to choose a single path, and in doing so it destroyed the wave-like nature that created the interference pattern. This is where the physicist John Wheeler came in with a brilliant and disturbing thought experiment, which was later performed for real. He called it the delayed choice experiment. He asked a simple question: what if we wait to decide whether we're going to measure the path of the electron until after it has already passed through the slits? Like, think about that for a second. The electron leaves the gun. It travels toward the wall with the two slits. At this point, it should have already decided whether to act like a particle going through one slit or a wave going through both. It passes through the slits. Then, after it's already on its way to the screen, we make a choice. We can either choose to put a detector in its path to see which way it came from, or we can choose to do nothing and just let it hit the screen. If we choose to put the detector in place, the experiment shows the electron behave like a particle. It went through one slit. If we choose to remove the detector and just look at the screen, we see an interference pattern. This means the electron must have behaved like a wave and gone through both slits. This is the heart of the problem. Our choice in the present seems to be affecting what the electron did in the past. When we decide to measure its path, it's as if a message goes back in time to the moment the electron was at the slits, telling it, hey, they're going to watch you. You better act like a particle and pick one path. When we decide not to measure, the message seems to be, coast is clear, go ahead and act like a wave and go through both. This result is so profoundly strange that it makes most people's heads hurt. It seems to completely demolish our common sense notion of cause and effect. How can an action we take now determine a past event? This is where the idea of retrocausality comes in. It's one possible, though controversial, way to make sense of this. The retrocausal interpretation says, yes, what we're seeing is real. The future event, our choice to measure or not to measure, is genuinely influencing the past event and the electron's behavior at the slits. It's not that information is traveling back in time in the conventional sense. It's that the universe doesn't necessarily follow the simple A then B causal chain we're used to at this fundamental level. Of course, many physicists are very uncomfortable with this idea. It feels like cheating. It opens up a Pandora's box of paradoxes. The most famous is the grandfather paradox. If you could influence the past, could you go back and prevent your grandfather from meeting your grandmother? If you did, you would never be born. But if you were never born, you couldn't have gone back to stop them in the first place. It's a logical contradiction. Because of problems like this, scientists have come up with other ways to explain the delayed choice experiment that don't rely on retrocausality. None of them are entirely satisfying, and they all have their own strange implications. One popular explanation is the Copenhagen interpretation, which was developed by Niels Bohr, one of the founders of quantum theory. This interpretation essentially says that it's meaningless to ask what the electron was doing before we measured it. It wasn't a particle or a wave, it was in an undefined state of potential. Reality isn't real in the way we think it is until we observe it. The entire system, the electron, the slits, the detector, the screen, is one big interconnected quantum system. Asking what the electron did at the slits before the final measurement is like asking about the sound of one hand clapping. The question itself is flawed. In this view, there's no backward in time influence, because there was no past event to be influenced until the whole experiment was complete. Another idea is the many worlds interpretation. This one suggests that every time a quantum measurement is made, the universe splits. When the electron reaches the slits, the universe splits into two. In one universe, the electron goes through the left slit. In another, it goes through the right. When you make your delayed choice, you're just finding out which of these universes you happen to be in. In this view, there's no retrocausality because all possibilities actually happen, just in different, parallel realities. We only experience one of them. This solves the problem, but at the cost of imagining an infinite number of parallel universes being created every fraction of a second. Then there's a more straightforward but philosophically challenging idea called superdeterminism. This says that the whole thing was a setup from the very beginning. There is no real choice. The way the electron was going to behave and the choice you were going to make with the detector were all predetermined and correlated from the moment of the Big Bang. It's all one giant interconnected system playing out a script that was written billions of years ago. The electron didn't know you were going to measure it, and the measuring device were always destined to behave in that specific correlated way. This saves causality, but it completely destroys the idea of free will. Your choices aren't choices at all. They are just another part of the cosmic clockwork, so where does that leave retrocausality? It's still on the table. Some physicists, like John Cramer with his transactional interpretation, have developed models that explicitly use backward-in-time influences. Cramer's model pictures a quantum event as a handshake through time. The emitter of the electron gun sends out an offer wave forward in time. The absorber, the detector on the screen, sends a confirmation wave backward in time. The transaction, the actual event of the particle traveling, is only completed when this handshake between the past and future is made. In this view, the backward-in-time component isn't a strange anomaly, it's a necessary part of every quantum event. Another way to think about it that makes retrocausality feel less paradoxical is the block universe model of spacetime. This idea comes from Einstein's theory of relativity. It suggests that time is not a flowing river, but more like a solid block. The past, the present, and the future all exist simultaneously. They are all just different locations in a four-dimensional block of spacetime. Our consciousness moves through this block, giving us the illusion that time is passing. But from a God's eye view outside the block, everything is already there. If the block universe is real, then cause and effect are just relationships between different points in the block. The idea of an effect happening before its cause becomes less nonsensical. It's not that the future is reaching back and changing a fluid past. It's that two events, one in our future and one in our past, are simply part of a static pattern that exists all at once. The relationship between them is fixed. The delayed choice experiment, in this view, isn't showing the future influencing the past, it's just revealing a pre-existing correlation between different points in spacetime that we, with our limited perception, interpret as a backward influence. It's crucial to understand what retrocausality is not. It does not mean we can control the past. All these quantum experiments show is a correlation between a future choice and a past event. You can't use this to send information. Imagine you and a friend are trying to use the delayed choice experiment to send a message. Your friend is at the slits, and you are at the detector, making the choice. You agree that measure the path means 1, and don't measure means 0. You try to send a message back in time to your friend. The problem is, your friend at the slits has no way of knowing what choice you made. When you choose to measure, they see a particle go through one slit. When you choose not to measure, they see a particle go through one slit. The wave, behavior only shows up later on the screen as a statistical pattern built up from thousands of electrons. Your friend can't look at a single electron and say, that one behaved like a wave. They have no way of decoding your message. The influence, if it exists, is hidden in the statistics and can only be seen after the fact when you both get together and compare notes. The universe seems to have a built-in protection against paradoxes. You can have spooky correlations, but you can't have a time travel telephone. So, we come back to the original question. Can an effect actually happen before its cause? The answer is a deeply unsatisfying maybe, but not in the way you think. In our macroscopic world, the world of people and planets and broken glasses, the answer is a firm no. The arrow of time, driven by entropy, is a real and powerful feature of our reality, because always precedes effect. But in the quantum world, the picture is much murkier. The very concepts of cause, effect, and even before and after become fuzzy. Experiments show us that a choice made now can be correlated with an event that, in our classical way of thinking, has already happened. Whether you interpret this as a genuine backward influence, retrocausality, a collapse of reality upon observation Copenhagen, a splitting of universes, many worlds, or a grand cosmic conspiracy superdeterminism is, for now, a matter of philosophical taste as much as scientific fact. All these interpretations are consistent with the experimental results. They just offer different and equally strange pictures of what reality is. The idea of retrocausality is appealing to some because it can feel more elegant. Instead of inventing countless new universes or denying the existence of reality before measurement, it simply proposes that time might not be the strict, one-way street we assume it is. It suggests a symmetry between past and future that is often present in the fundamental equations of physics. If retrocausality is real, what does it mean for us? It doesn't mean the future is completely fixed. In some models, it's more like the future creates a set of conditions or constraints that the past has to be consistent with. It's like solving a puzzle. You might know what the final picture looks like, but you still have to figure out how the pieces fit together. Our actions in the present are still meaningful. In fact, they could be seen as even more meaningful, as they might be shaping reality not just forwards, but backwards as well, locking in the very past that led to them. This is a deeply strange thought. It suggests a universe that is far more interconnected through time than our intuition allows. It paints a picture of reality as a self-consistent whole, a loop where the end is in some way tied to the beginning. Our concept of free will gets complicated. Are we making choices, or are we simply playing our part in a pattern that must exist in a certain way for the universe to be consistent with itself? The debate is far from over. Physicists are still designing new experiments to try and poke holes in these different interpretations, to find a crack that lets one view shine through as more likely than the others. For now, the question remains at the edge of our understanding. The fact that we can even ask such a question and that our experiments give us such baffling answers is a testament to how little we truly know about the universe. We live our lives on a thin crust of classical, common-sense reality, but beneath that crust lies a quantum world that operates on principles that defy our everyday logic. In that world, time may not flow, it may just be. And cause and effect might not be a simple chain, but a tangled web that connects everything, everywhere, and everywhen. So, can an effect happen before its cause? Maybe the question itself is the problem. It assumes a before and an after that might not be so fundamental after all. It's possible that in the deep structure of reality there are just events, and the relationships between them are far richer and stranger than the simple one-way street we call time. The window isn't breaking before you throw the rock. Instead, the throwing of the rock and the breaking of the window might just be 2 points in a static, pre-existing pattern, a pattern that is so weird and interconnected that it can look, from our limited perspective, like the future is whispering back to the past.